You're watching scientific film, observations of the northern lights, the aurora, captured by one of the world's most sensitive television systems at the University of Alaska's Geophysical Institute in Fairbanks.
I'm Pat Moore. During the next half hour, the people here and I will show you how science looks at the aurora. We'll talk about the patterns that the aurora makes in the night sky. We'll talk about the light emitted by the aurora, and we'll talk about the latest research in the magnetosphere. That's a huge magnetic bottle that surrounds the Earth's atmosphere. We'll be looking at a rocket range and a unique radar that lets scientists send probes into the aurora and look at it directly with the radar.
Probably, if you live in the north, you've seen aurora something like this, but the views scientists use are sometimes quite different. During the first few seconds of this film, you saw pictures of the aurora taken from almost directly underneath, looking straight up. They were taken with a super-sensitive television system. The lens used is telescopic, optically about 100 millimeters long. The view it sees looks like this. The camera looks through very narrow optical filters which isolate the individual colors of light in an auroral form. The naked eye cannot see these colors and motions since they are very faint and masked by the strong green light. The bottom of this aurora is about 70 miles above the Earth. Here's another way of looking at it. The all-sky view was first achieved with a fisheye lens mounted on a movie camera, which was modified to take 1 picture per minute of the night sky. Each exposure was several seconds long. All sky cameras are still used, but the newest technology fits the high-sensitivity television camera with a fisheye lens, and the pictures come out like this. North is at the bottom, and the edges of the picture are just above the treetops from horizon to horizon.
Probably the biggest reason it took 1,900 years to get a picture of what the aurora is doing on any given night is because of the lack of an overall view. It was primarily the work of Dr. Shinichi Akasoku that established that picture.
During the International Geophysical Year 1957-58, there were more than 100 cameras operating in Canada, Alaska, Scandinavia, and elsewhere. I decided to see what the aurora looked like from those sites at the same time. This wasn't easy. The Russians used different film and took their pictures at different rate than we did. And Swedish data were taken differently too. But finally, we set up several projectors, and by examining the film frame by frame, we began to see what was happening over the entire polar region on any given night. This was a pattern that started to emerge. We've known for a long time that the aurora activity was very strong during the magnetic disturbance known as the magnetic storm. We soon began to see in this room that storm was divided up into shorter cycles of activity, substorms.
The aurora follows a definite pattern throughout each night. Once again, we're looking straight up through the television fisheye lens. What we're seeing is called the quiescent phase of the substorm cycle. Those long auroral arcs encircling the geomagnetic pole are faintly visible from the ground. The bottoms of the arcs are between 70 and 100 miles above the Earth, and the tops extend up to around 250 miles. Near local midnight, we see one of the arcs becoming brighter. Until now, the light in that arc was largely excited by hydrogen nuclei, protons, with a net positive electrical charge coming into the atmosphere. The arc brightens when it receives a heavy bombardment of electrons. We're seeing about 1,000-fold increase in brightness. Within a few minutes, the substorm expands westward, eastward, and toward the pole. This is called breakup, or the expansion phase of the substorm. Within about 10 minutes, the expansion plays itself out, and the aurora begins breaking up into patches of drifting auroral forms. If it's an active night, the aurora may form once again into those long, faint bands, and the cycle may repeat. Here's what the aurora looks like on a global scale. We've assembled pictures taken over several days from an Air Force satellite which orbits about 600 miles up. To tell us about larger cycles of auroral activity, here is Dr. Bill Stringer.
To understand how the aurora behaves, it's useful to think about the fact that the Earth actually turns on its axis in space with respect to the Sun. The aurora is always situated in an oval over the Earth that stays fixed with respect to the Sun and has its center up here at Thule, Greenland. The effect as the Earth turns with respect to this fixed auroral oval is to move the aurora north and south. I'm going to illustrate that with this smaller globe here, where I've indicated Thule, Greenland, and we're going to refer to the aurora in Alaska over here. To aid in this illustration, I've made a auroral oval on this plastic overlay. This is the center of the auroral oval about which it'll turn. The daytime side of the oval is this narrow part up here that's close to the center, and the nighttime side, which is much broader, is located further away from the center of the oval. The oval again turns about Thule, Greenland right there. We'll place the center at Thule and keep track of what happens in Alaska over here. This situation represents about 6 o'clock in the evening, where the aurora is still north of Alaska. Now, as the Earth turns, the oval is brought down over the state to where, by mid-evening, you can see aurora from practically everywhere in Alaska. Now, the auroral oval actually expands and contracts, and what we're representing here is a slightly greater than normal magnetic activity. On other nights, the auroral oval may expand up to where you can only see aurora maybe on the north coast of Alaska. However, there are a fair number of evenings throughout a year where the oval is this size. Then later on in the evening, as the Earth turns, the oval again retreats northward to where at around 6 o'clock in the morning, the auroral oval is up here on the north coast of Alaska, and then later on, around noon, the aurora is located about 500 to 800 miles north of Alaska.
We talked a few moments ago about light being emitted from the aurora. How does that work? Dr. Jerry Romick is an optical scientist at the Geophysical Institute.
Spectroscopes and spectrographs have been around for over 100 years. The first measurements on the spectrum of the aurora were made by Angstrom in the 1860s. This is a relatively new instrument as composed of mirrors, a grating, an electronic detection system, which allows us to look through the observer's dome at very weak light from the night sky. Visible aurora are caused by light being emitted from the various constituents of the upper atmosphere. Oxygen emits green light, which is the most prominent color in the aurora. Molecules of nitrogen and nitrogen molecular ion, which doesn't form at the Earth's surface, emit red and blue light. Hydrogen also emits minute quantities of light in the red and blue. The cause of the light is somewhat complicated. High energy particles coming in along the magnetic field lines of the Earth collide with the atoms and molecules of the upper atmosphere. These very energetic incoming particles raise the energy levels in the atoms and molecules that they hit. Orbiting electrons move into new orbits and move back to their old orbits within a very short time. They give off the energy that pushed them out there in the form of emitted light of a specific color.
This is Dr. Neil Davis, the Deputy Director of the Geophysical Institute. We've heard that aurora are caused by energetic electrons and protons striking atoms and molecules in the Earth's tenuous upper atmosphere. Where did those electrons and protons come from?
In addition to sunlight, there's a continual outflow from the sun of charged particles or plasma.
This flow is called the solar wind. It doesn't penetrate directly to the Earth because it is deflected by the Earth's magnetic field. Where the deflection occurs is called the magnetosphere. It acts as a gigantic magnetic bottle and tends to keep most charged particles out, but it traps those already inside or those that leak in from the solar wind. Now, the magnetosphere weighs only a few tons, but it is capable of storing a large amount of energy which it collects from the solar wind. At times, the magnetosphere grows unstable and then dumps energy into particle motion through a sequence of events not yet understood. We call that sequence the substorm. During a substorm, charged particles are accelerated. They are mainly electrons and protons. These particles spiral down along magnetic field lines and strike the atmosphere. This causes what we see as the aurora.
At this observatory west of the campus, the super-sensitive television system that shot the pictures of the aurora you saw at the beginning of this film is operated. We'll be back here in a few moments, but right now our story takes us about 26 miles southeast of here to Eielson Air Force Base. This Convair 990 is used by the National Aeronautics and Space Administration's Ames Research Facility to carry instruments for scientific observation. Hans Nielsen of the Geophysical Institute has observed the effects of the magnetic field surrounding the Earth using similar aircraft.
When I went to school, I learned that there was only aurora in the north. That's why they're called northern lights. But of course, that's not true. There's also aurora in the southern hemisphere. And we have been interested in learning the relation between the auroras observed in the south and in the north. And more exactly, we have been interested in learning whether the auroras occur simultaneously at each end of a magnetic field line. We call it the conjugate points, whether the auroras occur at the conjugate points simultaneously. To do this, we have flown aircraft similar to this one here, one over Alaska and another south of New Zealand. Here's a beautiful example of similar auroras observed over conjugate point.
The magnetosphere is invisible. Dr. Gene Westcott of the Geophysical Institute has been working with the Los Alamos Scientific Laboratory to inject barium ions into the magnetosphere and trace out the magnetic field lines.
Sounding rockets such as this are used to carry the high explosive shape charges to create fast jets of barium plasma, which can trace out the magnetic field lines at about 500 kilometers altitude. First you see the explosion of the shape charge. Then coming down, the very fast barium ions are coming out as a thin blue streak. All of these ions will travel many thousands of kilometers out along the field line. They'll also drift perpendicular to the field due to the electric fields.
This is the only university-operated rocket range in the world, Poker Flat, 30 miles north of Fairbanks. The range was started for an experiment in 1968 with the support of the National Aeronautics and Space Administration, Defense Nuclear Agency, the National Science Foundation, and others. The range supervisor is Neil Brown.
Placing a rocket into Aurora is not an easy task. We often wait several nights for the proper conditions to come along. The sound of a rocket going out could be quite startling to the public if they didn't know it was going to occur. So we do notify the local newspapers And the public in general has been very interested in the programs that have taken place from Poker Flat and have often observed the barium releases and the rockets going out of north of the town itself.
3 miles closer to Fairbanks, the Stanford Research Institute operates a unique radar which bounces radio signals off the Aurora. One of the Geophysical Institute people who works with this equipment is Dr. Bob Hunsucker.
The Chattanooga radar antenna, 88 feet in diameter, the receivers are very, very sensitive. They're much more sensitive than used in a normal radar. To give you an idea of the scale of sensitivity, the radar system sensitivity of the Chattanooga radar is roughly 1,000,000 times greater than that of a typical transistor radio of a small variety. The Chattanooga radar permits us to observe the ionosphere by returning backscatter of our transmitted radar pulse from small groups of electrons. The ionosphere, of course, is that region of the atmosphere that reflects radio waves also. And so when a large aurora occurs, it can affect radio communication very markedly. To give you an idea, we have displayed here a couple of tracings of Chattanooga radar data. What is plotted here is electron density profile as a function of height, 50, 100, 150 kilometers. And electron density increases this way. Here's a simultaneous all-sky camera picture. Well, the antenna was pointed toward the south, about 13 degrees south of the zenith. So in this case, there was an auroral arc north of the antenna, and the ionosphere was quite unperturbed. In this case, the auroral arc moved right into the antenna beam of the radar, and you can see how the electron density increased.
We're back at the Esther Dome facility a few miles west of Fairbanks. From here, rocket shots and aurora are observed on the super-sensitive television system whose pictures you saw earlier in this program. Tom Hallinan is one of the engineers who designed and built that system.
We use television cameras to study the aurora because of their high sensitivity. We can get motion pictures of the aurora that show all the fast motions, whereas with traditional photographic techniques, long time exposures were necessary. These cameras were specially built for us to our specifications to achieve high sensitivity, and then since getting them, we've made many, many modifications to improve the sensitivity further. We've also combined 3 of our black and white cameras to produce a color camera, which may well be the world's most sensitive, or one of the most sensitive color television cameras in the world. This camera is equivalent to having an ASA rating of 1,000,000 as compared to about 64 for typical color films. With this camera, we can get real-time movie pictures of the aurora in color.
Also at this facility, Dr. Jerry Romick and the optical scientists at the Geophysical Institute operate a scanning photometer.
These are the microwave transmitters that we use to send the data from the meridian scanning photometer and our communications to Poker Flat Research Range. This is the control console for the meridian scanning photometer, which we operate here at Esther Dome. It does essentially the same job that the instrument that I showed you at the Institute does. In this device, a mirror rotates and in effect points the telescopes along a path in the sky from the northern horizon to the southern horizon. This way, we can determine the brightness and position of specific auroral point.
What we'll see now is a particularly tricky part of auroral investigation. Using combined data from the Chattanooga radar and the Esther Dome facility here, the scientists will attempt to launch a rocket carrying an electron trap directly into an arc of the aurora. If the rocket hits its target, variable electric fields within the counter's chamber will sort out electrons of different energies and allow them to be counted. This device measures a slightly different aspect of auroral electrons than the Chattanooga radar. Dr. Bob Hunsucker.
The most powerful techniques we have really are the complementing of various different techniques for observing the aurora. It's somewhat like the old story of the blind man and the elephant, which originated in India. Each blind man, as you remember, saw a different part of the elephant and judged what he saw of the total elephant from what his own experience. Similarly, with looking at the aurora, if we use a combination of many different techniques and put them all together, we can get a very much clearer picture of what the aurora is really like.
Attention all stations, on my mark, we'll be picking up the count at T-minus 5 minutes and counting on pad 3.
Mark, T-minus 5 minutes and counting on pad 3.
Jerry, on you guess you don't. This is Neil. What are you seeing?
The arc in the south looks like it's increasing in brightness, Neil.
Thanks, Jerry. Tom Hallinan, Esther Dolan, this is Neil. What do you have?
Well, the southernmost arc has brightened up quite a bit in the last few minutes. We could be a little bit late.
Neil Davis, Esther Dolan. This is Neil Brown. Do you want any holds?
It looks good. Keep counting.
Chattanooga radar, Bob Hunsucker. This is Neil Brown. What's the U layer look like?
I would estimate about 3 times 10 to the 5th electrons per cubic centimeter.
On my mark, T-minus 4 minutes and counting on pad 3. Mark, T-minus 4 minutes and counting on pad 3.
This is Poker Flat. We're at T-minus 4 and we picked up the count. Are we still clear for a launch into zone number 3? Thank you very much. We'll call you when it's down. NASA radar, what's your status? Chattanooga TM?
TM's go.
Payload control?
On my mark, T-minus 3 minutes and counting on pad 3. Mark, T-minus 3 minutes and counting on pad 3.
Blockhouses, is Joel request permission to go to pad 3 after booster impact?
Roger, stand by. Okay, thank you. Roger. Down. No.
Barry?
Yeah.
You have an update for the launcher settings?
Yeah. 27.4, 77.3, that's zone 3.
What are effectives?
On my mark, T-minus 2 minutes
25
and
and
counting on
78.
pad 3. Mark, T-minus 2 minutes and counting.
Bo, check with the roadblock.
Roadblocks 1 and 2, be advised, we're at 2 minutes and counting. 2 minutes and counting.
Roger, roadblock 1. Roger, roadblock 2.
Neil Davis, Esther Dome. This is Neil Brown. How's it looking?
The aurora's moving around a little, but I think we're okay. Jerry, what are you reading?
The intensity's holding pretty constant, Neil, about 45 kilorays, so it looks okay.
Chattanooga radar, Bob Hunsucker. Neil Davis here. What's it look like?
Same electron densities as before.
Go ahead, Neil. Count it down.
On my mark, T-minus 60 seconds and counting on pad 3.
Mark, T-minus 60 seconds and counting.
Seconds. 40 seconds. 30 seconds. 20 seconds. 10. 9, 8, 7, 6,
5,
4,
3, 2, 1, lift off.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14,
First stage looks really good.
16,
17, 18, 19, 20.
We see second stage ignition.
22, 23, 24, 25, 26, 27, 28, 29, 30 seconds.
Still looks good here. Chattanooga radar, what have you got?
Holy smoke, we're reading 5 times 10 to the 5th electrons per cubic centimeter now.
40
Thank you.
seconds.
Jerry?
It's holding steady at about 50 kilorays, Neil.
First stage is impacted. First stage is in. You're clear to go to the pad. All stations, the first stage is impacted. Second stage burn looked good. It looks like we've got a real good experiment.
Doors are off. Boom deployed. Oh boy, you got some data now. Went right through the arc.